Hi there. We are talking about section 3.4, optimization and elasticity of demand. First video, we're going to attempt to talk about using the extreme value theory, extreme value property to find absolute extrema. Okay, so let's get a definition out of the way. We've talked about relative extrema, so that encapsulates both relative maxima and relative minima. Absolute extrema are basically what we've always wanted an extremum to be. It's the largest value on any particular region that we might want. So for instance, usually we're discussing the entire domain of the function and we say which value is the largest. But we could always restrict to some interval and say what's the largest value of f on this interval. Okay, so that's what this means. There's the actual output. F of c is the maximum thing. The input c is the value that gets us there. So if this is f of c is an absolute maximum if it's larger than or equal to every other value in this interval that we're considering. So an absolute minimum is the same deal, except for minimum, of course. So now we just reverse the direction of this inequality. So now instead of f of c being greater than every other point, f of c is now less than or equal to every other point. So just a quick example from a picture. We've got our function defined on, it looks like from 1 through 12, maybe it continues on. But if this is all the picture that we've got, then this value in the top left corner is the location of the maximum. So at x equals 1, it appears to have a maximum of about 7. And then the minimum actually occurs either at this little relative minimum down here or at this rightmost endpoint. They're actually at the same height. So the absolute minimum is a value of 2. It just also happens to occur at two different points, x equals 6 and also at x equals 12. So there's actually no stipulation that we can't have an absolute minimum occur in more than one place. Because remember, all we're really saying is that 2 is the absolute minimum. This is the lowest value that we get to, regardless of how many inputs get us there. So the extreme value theory, extreme value property, that's the second time I've wanted to say that instead, tells us that if you want an absolute extremum on some closed interval, then you look in one of two places. You either look at critical points, which we've already done. This is where the derivative is 0 or it's undefined, but f is defined. Or you look at an endpoint. And that's actually the new thing that we're bringing to this. So all we have to do is find critical points, but then we also have to compare endpoints when what we want is an absolute extremum of some function. So let's try this with a formula rather than just a picture. So we want the absolute extrema, so that is the absolute max and absolute min of this function on the interval -3 to 1. And notice there's no if they exist kind of question. If we have a closed interval, the extreme value property tells us that there's going to be a lowest value and going to be a highest value. So as long as this function is continuous on the interval and the interval is closed, then that will be the case. Okay, so basically we need to find critical points and endpoints. And then all we do is figure out what the outputs are at each of those candidates, pick the biggest one to be the max, and the smallest one is the min. So the hardest math piece that we have to consider is finding the critical points, and that involves the derivative in this case. So f prime is the derivative of x squared over quantity x minus 2. And since we've got variables in top and bottom, it's hard to get away with without using product rule here. Or quotient rule. We could get around this, as always, by using product rule and chain rule together, but I think the logical choice in this case is the quotient rule. So low d high, high d low. So x minus 2 is the denominator piece, derivative of the top is 2x. Then we subtract the top left alone, derivative of x minus 2 is just 1. And then we get the denominator squared. Okay, so tidying up the top a little bit, we're down to just x squared minus 4. And then this is always a subtlety, but if we imagine basically we're going to multiply both sides by this term. Well, there is a little bit of subtlety in that we have to make sure that x was never 2, so we'll sort of keep that in the back of our heads. X equals 2 would make this expression undefined, and then we couldn't multiply both sides by it. But if it's a non-negative, a non-zero number, multiplying both sides by this is actually fine. However, 0 times stuff is still going to be 0 on the left side. So really, what we're solving is numerator equal to 0. Pull out a factor of 4, or a subfactor of x. We're left with x minus 4. And then we've got two solutions, x equals 0 and x equals 4. But one thing to keep in mind is that the interval that we were asked to look at is only -3 to +1. So x equals 4 is actually outside of that list of consideration. So we're not going to use that as part of our answer since it's outside the interval. So really we've only got one critical point to consider, x equals 0. So basically we've got three candidates. We've got the endpoints, -3 and 1, and we've got our critical point at x equals 0. So all we're going to do basically is take those values, those x values, and plug them back into our original f. So not f prime or double prime or anything crazy like that, just comparing the actual heights of the graph. So if we plug in -3, 0, and 1, these should be our outputs. And then we're ready to make a decision right at that point. We look for the smallest value along this list. So -1.4 is the lowest number. That must be our absolute minimum. And then similarly for x equals -1, let's see, this one's sort of in the middle. And then at x equals 0, then we've got an output of 0. And although it seems odd to have 0 be a maximum value, everything else is negative. So this is actually our smallest. So what we conclude is that absolute max is at a value of 0, so that's the output, attained at x equals 0 by coincidence. The absolute minimum is -1.4, that's the output, and that's attained at x equals -3. So that gives us an idea of how to find an absolute extremum, either from a picture or from a function like we just tackled. We'll be back in the next video to talk about a couple of special circumstances where we optimize in economics. See you then.